I mean, hopefully it will be Spark related, especially based on what I heard from the previous talk. But I may need some help to make that happen. So let's talk about high-performance builds and how we turn builds into a distributed system problem. And actually, I'm going to go on a short tangent, because I think the previous talk was very interesting. It was all about parallelizing jobs in installations and in builds in general, and having this composite model for parallel execution where multiple builds can communicate and coordinate in terms of parallel execution. And it's very cool, but we're still limited by how many cores we have. So this talk is about how we turn that 16 cores at -j into -j 500, 1,000, 10,000, because then it's much, much faster. So who am I? My name is Antonio Di Stefano. I'm a DevX engineer at EngFlow. And as I say, I work on distributed builds. My focus is usually on Bazel, which got some like bad coverage right now during the previous talk. Yeah, sadly, it does not implement the job server, neither as a client or as a server. I'm very passionate about rubber ducks. It's a fun fact about me. I don't know when it started or why it started, but at some point I just started getting some random rubber ducks by friends, colleagues, and literally random people. And now I have a rather large collection of a few dozens. Don't ask me any questions about this. I don't know why, but it's a cool fact. So first of all, what is a build system? I want to go back to the basics for a second. And from a technical point of view, a build system is just a function that takes your sources, your configuration, dependency, all of these inputs, environments and tool chains, which are also some kind of inputs, and turns them into a useful output, right? Each transformation happens via task or a series of tasks. Tasks can be combined, but more importantly, they can depend on each other, and that's usually represented through a direct acyclic graph. Now, that's very cool and all, but the most important thing is that a build system is a mean to an end. That end is our code can run and be tested. And in that perspective, the goal is to make the build systems as fast as possible because they impact our daily productivity, right? They can impact us when setting up a machine because you have to install dependencies from spec, but they can impact us in our daily development when you're changing one dependency and suddenly you have to recompile your whole monorepo or like large repos, right? We don't want that. And if we have to do that, we want that to be fast. And that fast does not happen locally, right? You have the first thing you have complex dependencies, right? Very few projects just depend on themselves, and very few dependencies. Most projects, especially in some ecosystems, they depend on a universe of dependency, and that universe is extremely broad, and you're out of control when it comes to it. You still have to build it, though. It's necessary for you to build it. And then you're limited by hardware constraints. There's the CPU, which is the most obvious one, right? That's where we pass -j, right? But there's also the RAM. There's also the local storage, and even the network, right? Everything in your system fights against making builds fast. So as long as you keep it on one system, builds are never really going to be fast. Caching is fragile. Oftentimes, caching is on a per package or per build level. Some projects make it better, like Ccache is on a task level. A single command can be cached. And it's quite efficient in doing that, but it's limited to C and C++. It cannot cache tests. It cannot distribute tests. It cannot distribute compilations. It cannot even do linking. So we need a bit of a more generic approach. And all of that eventually builds up to creating developer latency. As I said, and as the XKCD comic illustrates, our favorite pastime when the build is stalling behind is just to play around or just wait. And that's not very productive. And it's even more productive in this new world of agents, right? Agents are only bottlenecked by the pipeline we create in front of them. Otherwise, they're much faster than humans, right? We're limiting them. If you can produce 1,000 lines of code, but then it takes an hour to run a test, they're not much faster than humans, right? So we create a productivity bottleneck that we share with machines now. So when the local environment cannot do it anymore, that's where you look outside. And outside is just more machines, possibly in someone else's data center or in yours, but just more machines. So if we treat compilations and linking and all the build system problems as a distributed problem, then we can scale it horizontally, right? Every command can run individually. A compilation does not need another compilation to run, right? And so as long as we keep track of the dependency graph we looked at before, we can run a lot of things in parallel. We already do. We just use a small number for -j. We decouple the order. We can run J1000, but if the RAM is not enough, or if the disk is not enough, then you can have the most powerful CPU ever. It's still not going to be fast. But also, we can centralize infrastructure now. This distributed system can be shared by multiple people. You don't waste compute resources. When it's running your build actions, it's running someone else's build actions. And you may even run multiple builds from the same host at the same time because you do not use local resources, you use only remote ones, right? So let's say that you've got a shared instance that multiple developers have access to, and you want to install tools with multiple environments, multiple tool chains, and so on and so forth. You can run all of these things in parallel as long as you run them somewhere else, and you just fetch the artifacts that you need at the end. That's the power of turning this into a distributed problem. That now local resources do not matter anymore. You can still use them to some degree, you can leverage them, but they're not central and they're not stopping you anymore. And so that's where Google struggled a few decades ago. They had this problem. Google has historically this huge monorepo. And when I say huge, I mean huge. Like, it's probably larger than all the code bases we've worked on combined and then multiplied by a really large factor, right? And this scale of problems is very interesting because there's no way in which a Google developer can start the first day, get onboarded, pull the repo, build it, and finish their career in Google before the build is finished, right? By that time, they're either going to quit or be fired. So they need to distribute it. There's no other way around it. Google has taken a very extreme approach to this problem. They've reinvented their own build system, which was called Blaze. And the internal version is still called Blaze. But there is an open source variant, which you may have seen, especially with TensorFlow, called Bazel, which once again, sadly, does not implement the job server. If anybody wants to work on that, please hit me up. And the way that Bazel handles things is a bit more dramatic. First of all, it's a multi-language build system. It's very flexible, very extensible. You can make it do pretty much whatever you want. But it takes this extreme approach in making you declare carefully all of your dependencies, which makes it trivial to run something remotely. If you know what something depends on, all the files that it depends on, what command it's going to run, and what outputs it's going to generate, then you can safely run it remotely, right? You've isolated it well. But in most build systems, we don't get this advantage, right? Most build systems are glorified task runners that run on a tree rather than on just a list of tasks, right? And so we need to find a bit of a different way, but we can still do it. We can still do it with the same protocol. And this protocol is called RB, Remote Build Execution. It's a very creative name that it literally does what it says. And it allows you to run on a given set of inputs, an action, which is a classic Unix command, and get some outputs. Those outputs will be cached. And if you don't want to use the execution part, you can also just skip the execution and upload the artifact yourself. More like a normal cache for build systems. So let's see how it works. We're going to look a bit at the various moving parts, at the architecture of the system, because there's a few. The first one is the content addressable storage. So every blob in RBE, no matter what the type of blob is stored on this cache. It's always accessed by its digest. So, which means that if the file changes, that's literally a new file because it will change the digest. So there's no way to corrupt existing files that exist remotely and corrupt the cache. That's a really important property. The second component is the action cache, where we can basically reference a given action and its inputs to the outputs that it generated. It's what connects the cache with its caching capabilities. We need to find a way to reference those files just based on the command that will eventually create them. But what runs things? That's usually something, the two last components are a bit down to the implementation. Each implementation implements them differently, but usually they all kind of agree that there's two main components. One, which is the workers, the physical instances that will run things remotely. And the other, which is the scheduler, which is the facade of your RB. It's the one that gets all the calls decides to store on the cache or the action cache, whereas the workers are just doing the compute part. But the fulcrum of all of this is the action, which is a really complex thing, as you may tell from this graph. But we're going to get through it, and it's not going to look this complex anymore once we're done with it. So the action, as well as its components, it's a Merkle tree, which is a data structure where you store the content of the nodes, and you reference it by a chain of incremental digest of each node's content. So if any of the leaves changes, then the digest of the root node will also change. Right? I think I stepped on the cable. And so this property is important because if anything on the file system changes, or the command changes, or an environment variable changes, we have no guarantee that the output of the execution will be the same, right? Say that you have the same file system, and you have this command that looks at the variable magic number, and when it's 42, it emits a file. When it's not 42, it does not emit a file, right? In this case, changing the environment variable will change the output. So it's really important that if any of the property changes of this execution, we invalidate it, which is why this is a Merkle tree. The topmost part is relatively easy. The root of this action is the action itself. It's a proto message, like all the other components you're going to see. They're protobuf messages serialized and then saved on the cache, right? So just normal blobs. They just have more meaning when you use them for execution. And the first thing that an action has, well, action has two things: a command digest and an input root digest. So the command digest is the message that is going to execute. It's a reference to the message that is going to execute things. So what command I'm using, the args, the environment, and also one thing that I'm missing here, because it would take too much space, the declared outputs. If we want to cache things, we want to know what are we caching, and that's usually done in the command. The second part, which is a bit more interesting, is the input root, which is a sub-Merkle tree. It's Merkle trees all the way down. And it's very simple. It has files and directories. Directories are other directory proto-messages that are serialized on the cache. And once again, they're referenced by their digest. And files are also digest that reference files that are uploaded to the cache. But those files are stored as is, rather than being references to other messages. And this directory is meant to, this structure is meant to be recursed when you execute things. So when a worker comes by and you tell it, execute this action, it's going to fetch this tree and stage it on the file system. I omitted one attribute that I forgot about. Directories have names. And when you restructure it, you pull all the files and you rebuild the directory structures. You can also do so lazily. So some implementations do this at runtime through a fuse file system, which means that you can also run an action without actually having the contents of the file system and delegate that to later stages. So how does this all run work? Try to present it in a bit of a different way. I start with the diagram, realized this is bad. It's too many things. I made it smaller. This is not the original one. It's not complete. The complete one will last a few slides. And then I don't think that's tenable. So I have like a smaller version of it, but also like a pseudo implementation of the client. And I'm going to walk through both of them at the same time. And the first thing, which is not even present on the sequence diagram, is we serialize all of this stuff. All the messages we've just looked at, we have to turn them into blobs, right? In memory, they're just protobuf messages. They have to turn into physical blobs we can send to the remote system. So we serialize the input tree, we turn it into a tree rather than just a more abstract sequence of directories, right? Because the API could literally just say, I want dot to be uploaded, and then we need to return it into a tree that is compatible with remote execution. We do the same for command, and we do the same for the action, which composes all of them. But then the next thing we do is we check if this has already run, right? If we've already run this action, we can find it in the action cache. And that could be either because there's been a remote execution, so this thing ran on a worker, or because a user ran it and they decided to upload it, which happens automatically, but it's a different part of the protocol. So if that happened, we just fetch the blobs, right? What's really interesting here is that in Bazel, you don't even necessarily need to do that. If you know the digest of a blob, you can fetch it whenever you need it. So there's a service called remote output service where you can literally bind a digest to the file on a fuse file system, and it will be resolved later. So you can run builds without having any I/O with this system. However, this is not something supported yet outside of Bazel, so I'm not going to spend too much time on it. But it is a possibility, and we're working on making that possible for other build systems as well. But what happens when you don't have that, right? So the first thing you do is you collect all the digests, and you check which of these digests are present on this remote execution cluster, right? And there's this API called find missing blobs, where you give it a list of digests, and it returns a list of missing digests. And with that list, you can tell, okay, I need to upload these files or these protobuf blobs to the remote system, and that's what you do next, right? You prepare things for execution. You prepare the file system, but you also prepare the structure of the execution itself. So it's data structure represented as file system, but also the file system itself. And then you get to the nice part, which is, it seems very simple from here. It's probably the most complex part on the server side. You basically go to the scheduler and you tell it, okay, can you execute this action? And the action is referenced by its action digest. Again, any mutation on the file system or the command itself will mutate the action digest. And when after it runs, you do the same thing. You can download the blobs, and then that action is gone. What's important here is that this does not happen at the build level. This happens at the individual command level, right? And it does not just happen on C and C++ compilations, which is its strength compared to something like Ccache or DCC, right? This protocol, you can use it, and it's already used for other languages and other tools. So for example, you could use it to compile some Java. Hopefully not, but if you have to, that's an option, or other languages. One really interesting thing, and that's I think where we're missing a lot of value, is that this protocol is so generic that you can use it to run tests, right? And tests are the part of the build where, like, I think the existing ecosystem in the C and C++ world is kind of lagging behind, because tests are perfectly parallelizable. Tests do not depend on each other. So why are we running them serially? They are the most parallelizable part of the system, and they're also the part of the system that is most likely to be invalidated by any change, right? Because if you change any of your code, you need to run a much larger suite of tests. And so computationally, we are skipping the most compute-intensive part, which we should be distributing, but we're not, right? And that's something that, again, in Bazel you get for free, because the build system is built around it, because otherwise Google would not work. But with other systems, you need to have a tool that allows you to do so. I think something is broken. Additionally, you can also create your own tools. This is something that, my company, being experts of RB, we do fairly often. We build tools that are not build systems, but can benefit from distributing execution, right? So for example, you could build a tool that allows you to debug when execution failed, or you can build a tool that is not part of a build system, but runs some really large integration tests, and in which case, you don't want them to run serially, right? You want them to run in parallel as much as possible, because each may last an hour or so, right? So you can also build your own tooling. It's not necessarily something I recommend. Stay in the build system land as much as possible, but if you want to dip your toes into remote execution, understand at a deeper level how it works, that is indeed an option. There's SDKs available, and the protobuf definitions of the protocol are publicly available under Bazel build/remote APIs. But what I want to look at is this tool called Reclient, which I think is really cool. So Reclient is a generic Ccache-like wrapper for invocation. So you can use it the same way you use Ccache, right? You prepend it to a command, or you create a symlink that or you create a script that replaces the command, and that approach works too. And Reclient does something really smart. When you look at another build system that is not Bazel, you don't necessarily know all the inputs of an action, right? You may be running GCC on this specific source, but this source includes 20 other sources that have not been declared in the command, right? That's pretty common. That's how things normally work in any other build system, right? So how do you know the inputs for remote execution? So the most important bit of Reclient is that, one, it's aware of the type of the invocation, and it does so by something called labels. So if you want to remote a GCC compilation, you tell it, this is GCC, it's a compiler, and you run it this way. And the second part is this component called scandeps, a dependency scanner, right? It's this long-lived daemon that parses the sources and actually executes the macros. It expands them. And then it looks at the includes that come out of it, and it makes them the inputs of the action, right? So instead of pre-declaring them manually, which is what you do normally in Bazel, you discover these things at runtime. And it's relatively fast, it's well cached, well optimized. And it allows you to kind of make up for the lack of declared inputs from foreign build systems that don't do so. And when you do that, then it's pretty much equivalent to be able to run things on Bazel, right? You have the inputs, which was the missing thing. Scandeps will also look at the outputs, right? Will tell you you're actually generating these outputs, and so does Reclient. It's a multi-phase process. And when you have the inputs, you have the outputs, you have the environment variables, which are easily accessible. Then you can run something remotely, even though your build system does not support it yet, right? So the way we get around it is the same way the Ccache does it. And one of the many ways of configuring it is through these config files, key equals value kind of format. There are two components to Reclient. One is basically this long-lived daemon called reproxy, which intercepts all the commands. It's centralized because it allows us to limit the resources that we use, control concurrency, but also potentially deduplicate downloads and uploads, right? Because all these invocations are individual, they're separate, they need to find a way to communicate and say, okay, we're actually downloading the same blob, right? You know it because it's, you have the digest of it. It may be on different paths, but why would we duplicate the network load, right? And so it's something that the proxy is responsible for. And the re-wrapper, the component that you end up actually using as a wrapper for your command, that's just pretty dumb, does nothing else but call reproxy, and then reproxy does all the heavy lifting, right? And sometimes things may still not run remotely. So Reclient has been pretty smart in allowing you to say, if remote doesn't work, fall back to local execution. And even then, you can still upload the local execution results to remote cache. There's an additional mode, which is racing mode, which answers one additional problem. We still have a machine running locally. And if we run things just remotely, we're wasting compute, the local compute, right? Why not use it? So you can actually have this racing mode where you can race remote execution and local execution, and the first to come wins, right? So you don't even waste the local resources anymore. It's optimizing compute as much as you can. However, this will result in additional network throughput because you need to upload the output results. So it may not be necessarily the best strategy and does require some tuning, because if you're running multiple builds at the same time on the same host, you don't want one of them to just consume all the resources or make the machine unusable, right? Once that's done, once we've run things remotely, we basically just write the outputs like normal remote execution would entail. We report the exit code, and then it just looks like a normal process. To the caller, the build system in this case, this just looks like calling GCC or Clang or anything else, right? It's just that it did not run locally. It runs somewhere else, possibly in the cloud. So this is an open source centric conference. And I work for a closed source implementation of this protocol. So I want to give you some options. You can follow this link, of course, in the Bazel wiki about remote execution services. Oh, I need to speed up. And there's multiple options. One that I really like is called Build Barn. It runs on Kubernetes, it runs on Docker Compose, and if you have a fridge, it probably runs on that too. Completely open source, very cool project. I'm not endorsing it because I work for a competitor, but if you want to try an open source option, you can use that one. It's very well written, very well implemented, so I highly recommend it. And with that said, before my laptop shuts down, questions?
Thanks. That was very cool. I'm curious. So this whole time you're talking about digest, right, to identify things in the cache. Is there some kind of thing that you do for that these things do when there is a collision for hashes? Like digest can collide, right? They're fixed length things.
So I said digest, but it's digest plus length, and you can even change the algorithm. Of course, it depends on what the server supports. The most common one is SHA-256, but there are other implementations that use a digest too. But basically, the way we avoid it is digest plus length. And when you got SHA-256 and the length, it's really unlikely that you're going to have a collision.
But you're talking about like Google scales, right? Like, or at least Basil was motivated by Google's,
yeah.
And at Google scale, like unlikely becomes like weakly, right? Shouldn't it at least?
A SHA-256 is outside the realm of possibilities for a few billion Googles.
Okay.
You're more like atoms in the universe.
Makes sense.
Yeah.
Okay, so that was really interesting. If I understand this correctly, so SPAC is Merkle trees too, like the hashes are Merkle hashes, and we're basically generating package installations from inputs and installing a package output as a hash thing. But it's package granularity, and we can allocate packages to nodes, but we can't scale to like 1,000 things because there's not that many builds that have 1,000 packages, right? Is that how does Bazel manage this? My understanding is that like with a build system like this, you have to write the Bazel rules and the Bazel actions and all and that's the granularity of parallelism, right? And there is support for external dependencies, but that's a single task, isn't it? Or can you build an external dependency in parallel too?
I mean, let's not even talk about Bazel. Let's talk about like any other build system. Let's say you've got a CMake build that runs Ninja eventually, right? This protocol does not work at the build level like SPAC does, right?
Yeah.
It works at a command level. Okay. So let's say that you're installing an LLVM, there's dozens or hundreds of thousands of single individual compilations, which is why you can scale to 1,000. Or you can scale, I'm pretty sure that LLVM you can scale way higher than that.
Okay, so when's CMake supporting REAPI, Bill? That seems like it would be very cool.
I mean, I actually have a question for the audience. I'm not a SPAC expert, so if any of you would like to help me integrate this with SPAC, that'd be great. It could work as a backend for the build cache. It could work the same way you use Ccache, but also for other compilers. And it could do much more. Like you could use it for testing as well.
That's kind of cool. Yeah, I think that's interesting. Any other questions? Okay, awesome. Or do we have time for one more?
Yeah, so thank you for the talk. I noticed in one of your slides that you're hashing, or maybe you're hashing the command and the environment together. I was wondering if you could select what you hash from the environment, because sometimes you're in scenarios where you need an environmental variable influencing the build, maybe you're pointing to a license server or something that may change over time, and you don't want that to invalidate the cache. So I was just wondering if something like that's possible.
You can check already which environment variables are forwarded, or even edit the values, right? You have a lot of flexibility, and also you can go even deeper. You can even declare the environment. So one way in which most of our users get around declaring all the inputs and tool chains is just creating a Docker image where they can run these executions. And there you can also add environment variables that are specific to the runtime, right? Things that you cannot know up front because you don't know the execution environment of that command.
Okay, perfect, thank you.
You're welcome. You can kick me out.
So just on the previous question, no one has yet found a SHA-256 collision anywhere.
Yeah, so that would, but having the length is still useful because you know how large is a blob that you can fetch. So there's an advantage to that also for the implementers of this protocol. Sorry. Oh. Thank you very much.
All right, thanks.
All right, let's thank our speaker again.